I just got out of the shower. Not long ago at all. So that's why the whole wet shirt thing. Hello, everybody. Hello. Oh, y'all ever had those days? They're just weird. Different than the other days. Today was one of those days. It was just a abnormal day. And I'm glad we're past the brunt of it. So it's good stuff. Moving forward. Today is the last stream of the week. Tomorrow's Saturday. Well, technically today's Saturday. Is the 2nd, December 2nd. But it's late at night, as happens sometimes with this stream. But yeah, we are going to be doing this video, and we're going to be downloading these things. What is this? Is this a video? What? With this coding stuff, I've seen websites that I've never seen before. I've never seen a website like this. What is this? What am I looking at? Download? Am I supposed to download it? The increasingly popular Dropbox file archiving. So these are just... Okay, so these are just clients who use SQLite as the public domain. All right. Well, let's see.
Hello, and welcome to our chapter on databases. We're going to learn a lot in this chapter.
Relational databases and SQLite.
Learn a whole new programming language, SQL, and learn how to use that.
I'm sorry?
So you're going to need a new piece of software to run all of the exercises that I'm going to do called SQLite Browser. We're using a database called SQLite. Go ahead and download this. You might have to pause and come back if you like.
Okay, fair enough. Let's just, I don't know, right away. Wait a minute. Usage? Is this that's the same website? Oh. Download page. Okay, source code documentation. What? What do I do? Which one do I download? Hope he tells us.
Go to SQLitebrowser.org and download it and install it.
That's it? That's all you give me? Well, let's try the browser first. We'll just do the browser. Sponsoring us on Patreon. We'll do this one. We'll put it in coding. How about that? That would make sense. Look at all these exercises. Okay, hold please. Oh, come on. I have space. I know I do. There we go. Except... What? Cipher is a separate application. This page allows you to choose the shortcuts for each application and where to place them. Do I need to? Fine, we'll put them both there for now. Click the icons for the trigger to change the way features will be installed. That's fine. Shouldn't take long. Hopefully. Here we go. So what are we looking at? Oh, disregard that. Matter of fact, I don't even think I need that anymore. This is like for a job stuff. Where am I coding? Was it? Wait, hold on. Didn't I make shortcuts? I know I have like a crud ton of this. Oh, hold on a second. Well, shoot. Hold on. I'm gonna be right back momentarily. Okay, sorry about that. I had like 1,000 things up. But we have these now. What do I do with it? Oh my goodness. What? So let's get back into. So we have this now. Good. Homebrew. Oh, that's for Mac. I'm just kind of looking this over just so we can say we did. Skype. PHP. Google, Facebook, Apple, Adobe. Goodness. McAfee. Microsoft. They got the big boys on here. Amazon's not on this list. Other than that, they've got like the big. Disney, I guess, also is in the year. So I don't know what I need to source code. I feel like that's it, right? Documentation. Android, Linux, Windows. Is this what I need? We'll put that SQLite, hold on, light stuff. If we need it, we'll know where it is. And then we'll also do this. One of these, both of these. C source code as an amalgamation. Should I just do them both? I don't know. Auto config. Download product data for scripts to read. So Source code repositories. I think we have what we need. We'll leave that up. I don't know.
While you're doing that,
Sequential master update 1970s. Old sorted, new sorted. Merge, new sorted, transactions sorted.
we'll talk a little bit about the history. So, in the old days, 1960s, 1970s, I started doing computing in 1975. We didn't have a lot of storage. I mean, this is 16 gigabytes right here, and we didn't even have megabytes. I mean, the computer I had a few megabytes of stuff. So we didn't have a lot of disk drives, and so permanent storage was often sequential. And these tape drives that we had, tapes and tape drives were the scalable part of storage, because you could just make more tapes and you could rack them up, and so that was our way of greatly increasing the storage of the computer. The problem they had is they were sequential. You read it advances, read it, advance, read and advance. Now, interestingly, we've been writing programs that do this, that everything we've written so far pretty much reads the whole file, reads the whole web page, reads this, everything we read it either a loop or read the whole thing. And that's because we have plenty of memory, but we're still reading sequentially. And so the way you would do this when you didn't have enough spinning storage or online storage is you'd use offline storage, but the trick would be that you would sort it. So let's imagine that you're a bank and you have a bunch of accounts, only a few of which are active on any day, and you have a tape that has, in account number order from low to high, the prior balance, last night's balance of every one of your bank accounts. And you have a bunch of, let's imagine that you're a bank and you have a bunch of accounts, only a few of which are active on any day, and you have a tape.
Sorry, hold on. I think my wife was moving like up and about. Then I felt something too, like in the ground. I think we're good. Okay.
Tape storage, but the trick would be that you would sort it. So let's imagine that you're a bank and you have a bunch of accounts, only a few of which are active on any day, and you have a tape that has, in account number order from low to high, the prior balance, last night's balance of every one of your bank accounts, and then you do all the transactions and you record how much money was taken in or out for each account number, and then you sort those transactions. And then what you do is what we call a sequential master update, and that is you would write a program that would read the first transaction and hold on to it. Say, okay, this is account 45. Then it would read the first account, like 1, and it would copy 1, and then it'd read 2, and read like 7, 8, 42, 43, then it would read like 44, and then it would read 45, but it would change that and write the new 45, and read the next thing, and so this might be 60. And then it would read a bunch of stuff and copy a bunch of stuff, and then it would finally get to 60, and it would merge the add or subtract, and so the old balance ended up here, and the new balance did here, and you had to only make one pass through the data, so it was super efficient. So we had all these mechanisms to sort. We used to do punch cards and have sorters and all these things, and then those things would run for hours. And if you watch old TV shows, these tapes are spinning and these things are running back and forth. These are simply reading and writing tapes, and that's how we did a lot of data processing, because we could store far more on a tape drive than we could on a disk. And with racks of tape drives, we could scale the storage that our computers had. And so that's the way we did data processing, but it meant that the only way you knew what the old balance was it was the balance as of this morning before your bank started. You don't know what the balance was for the day, and that led to things like you can never you can never withdraw more than $100 a day or something like that, because you don't know what the old balance was, or you might go withdraw $100 at a couple of different branches, and so they weren't able to look your stuff up right away. Now, it didn't take
random access. When you can randomly access data, how can you lay out data to be most efficient? Sorting might not be the best idea.
along until the disk drives got better and better and better, and you could store the entire accounts, all the accounts and their current balances on computers. And then the problem becomes is what happens if sort of in the middle of the afternoon you want to update a balance? Well, do you want to read all your data and then write a brand new one? And say that takes like 10 minutes. That means for that 10 minutes, only one person can be updating their bank balance. And so because we could randomly access this data, we didn't have to read it all sequentially. The trick is how do you spread the data out, and then how do you make it so you can change a balance? This is, of course, second nature today, but how do you make it so you change the balance here without changing the balance there, and you can have multiple people going simultaneously to these things, and make sure that you can't say to withdraw money at 2 different locations simultaneously and somehow have your bank balance get corrupted by that. So there's a lot of debate on how to do that. And in early days, we just did sequential master update. But increasingly, we wanted to make better use of the random nature of our computers and our storage. And so that's what led to databases. Databases are the science of how you make use of rotating random access data, permanent data, in a way that allows you to read, modify, and update that simultaneously from many different locations and yet keep the data completely consistent. And so this led to a
relational database. Databases. Relational databases model data by storing rows and columns in tables. The power of the relational database lies in its ability to efficiently retrieve data from those tables, and in particular where there are multiple tables and the relationships between those tables involved in the query. Okay.
A study of a thing called relational databases. And relational databases are not the only databases that happened. We had many other kinds of databases, and there was a debate. And I remember in the 70s and the 80s, there was folks that says, oh, no, there you can do index sequential. That's the way to do it. And relational databases weren't all that popular the first time that I saw them. I didn't like relational databases. But relational databases had an inherent advantage because they were based on some really powerful mathematics. And the interesting thing is early on, the relational databases were slower, but eventually they figured out how to sort of bring all the cleverness to bear to make relational databases fast. And so relational databases are a pretty advanced technology. And
terminology. Database contains many tables. Relation or table contains tuples and attributes. Tuple or row, a set of fields that generally represents an object like a person or a music track. Attribute, also column or field, one of possibly many elements of data corresponding to the object represented by the row. Okay.
And there are companies like Oracle that are very, very wealthy, and their primary product for many, many years was nothing more than a clever database product, a clever piece of software that was really good at solving this problem. And that's how important this problem was to computing. If you read about databases, you're going to see 2 sets of terminology. One set of terminology comes from the mathematical background and has to do with the underlying math. Things like relations, tuples, and attributes. That's kind of like the fancy math version of it, and programmers kind of think of them as rows and columns inside of a table. And so if you look at sort of fancy...
Goodness me. A relation is defined as a set of tuples that have the same attributes. A tuple usually represents an object and information about that object. Objects are typically physical objects or concepts. A relation is usually described as a table, which is organized into rows and columns. All the data referenced by an attribute are in the same domain and conform. All the data referenced by an attribute are in the same domain and conform to the same constraints.
Theory, you'll see words that look like this, and they're just full of this and the connection. Now, all this is important and true, and if you really want to get good, you sort of begin to understand the nature that we model data at connections rather than at sort of intersection points, rather than just modeling data as a flat file the way we do. But for now, we're going to, as programmers, think of this rather than just modeling data as true. And if you really want to get good, you sort of begin to understand the nature that we model data at connections rather than at sort of intersection points, rather than just modeling data as a flat file the way we do. But for now, we're going to, as programmers, think of this as just like, oh, it's like a super fast spreadsheet. The super fast part is the math. For us, the rows, columns, and tables are spreadsheets. So think in a spreadsheet of sheets, sheet, and that's like a table, a named thing like tracks or albums, artists or genres. And then there is rows, and each row has a different kind of data. And then there's columns, and we sort of specialize the first column in many spreadsheets to say what's in there. This is not really the data. This is like metadata. It's like the title's in this first column. That's not really the data, and the data starts here. And we have different kinds of data like strings and numbers, et cetera, for each of the rows. And literally, you can get away with this as sort of about 80% of databases is just a really super cool spreadsheet. But under the covers, it is far more powerful than that. So one of the early arguments that
SQL, structured query language, is the language we use to issue commands to the database. Create a table, retrieve some data, insert data, delete data.
That happened was, again, what the programming model for this was. And a lot of folks wanted a programming model that reflected how the data was actually stored. The notion of structured query language came about in a way to express what you wanted to happen and allow that to be sort of a very abstract expression. Select all records that meet this criteria, not read. And so structured query language is not a procedural language. It is a imperative language where you're simply saying what you want, and then somebody writes the loop. The database actually does the loop, but it's a way for you to avoid actually writing the loop. Now that turns out to be the power of databases, because the cleverness in how to write the loop is a way that you would probably never figure out how to be most supremely optimal when it comes to writing the loop, as you'll see toward the end of joining many tables together and selecting and throwing array and getting down a count or whatever. Someone has figured out how to do that really, really well. So the idea is you would express, we're going to create some data, we're going to retrieve some data, we're going to insert and delete it. Create, read, CRUD, C-R-U-D. Create, read, update, and delete, CRUD. And so that's what this does. It's a language that does this very simply. Now the applications that we're going to use this for are more of a data analysis application. We've been doing data analysis through the whole course. And the kinds of things that we'll see in the remaining chapters is we'll take some raw data file. These might actually come across the network, and we'll write some Python programs to play with that data, parse it, clean it up, make sense of it, and then write it into a database. And this might be a slow process, or this might be really nasty, and this might be a way to have very clean data. And then we'll write another Python program to sort of read through it, and it's all efficient and pretty. And then we can produce files, and maybe we'll visualize it or do further analysis in R, Excel, or a JavaScript visualization framework. And so in this situation, you will be the person who is both sort of writing the programs, database administrator, and you can, using SQLite Browser, play and look at the database kind of in a raw way. And the first part of this, we are mostly going to be using SQLite Browser just to talk straight to a database. Later, we'll write Python programs that read and write data and visualize the data. So this is what we're going to do first, and then second, we're going to do this part right here. That's the second thing we're going to do. Now,
my dad's a database administrator. Web applications with databases. Application developer. Builds the logic for the application, the look and feel of the application, monitors the application for problems. Database administrator. Monitors and adjusts the database as the program runs in production. Yep, sounds like what my dad does. Often both people participate in the building of the data model.
Now, another really common use of applications, and something that if you continue learning more about programming, is that you will want to write an online application like Amazon or a company or Twitter that's got a website and it stores dynamic data in databases. And so the picture for that is similar but different than the picture we're going to start out with. And so the way this usually works is that you, the end user, uses a web browser, talks to the application, and the developer writes the application software, and that application software stores its data in a database. And inside that database, we talk to the database using SQL, and all the data is actually stored here, and the magic happens. The data server is that database software that's so precious and valuable. And then there's another person, often called the database administrator, who has access to the direct access to the data. And these roles in medium and large projects are kept separate, mostly because the production, while it's running and live, the developer leaves the data alone and works on, say, the next version of the software. And then the developer has a test version of the application that they run on their computer where they're doing all that stuff. And so this database administrator is a role in a large project where we have to run production and keep production careful, keep production in good shape. So the database...
This is so interesting, like, just... I've only heard this in context with my dad, and so it's interesting seeing it here. A database administrator, DBA, is a person responsible for the design, implementation, maintenance, and repair of an organization's database. The role includes the development and design of database strategies, monitoring and improving database performance and capacity, and planning for future expansion requirements. They may also plan, coordinate, and implement security measures to safeguard the database.
Administrator has this responsibility for the production aspects of the data, and you may be working in a situation where that you're not actually controlling the data. The database server is on different computers, you have little special access, and you write programs to sort of read the data, and so the database administrator is the person who is asked by the organization to administer that data. The data that we
database model. Database model or database schema is the structure of or format of a database described in a formal language supported by the database management system. In other words, a database model is the application of a data model. What? In other words, a database model is the application of a database model when used in conjunction with the database management system. A database model is the application of a database model when used in conjunction with the database management system.
Develop, and we'll do this in the second part of these lectures, conforms to a data model. That's the metadata. Is this an integer? Is this a string? You know, how many columns is this? And the data model turns out to be very, very important, and there's a lot of science to building an effective data model that leads to really good performance. And it's a collaborative activity between the application developers and the database administrator to make it so it's efficient, runs in production, et cetera, et cetera, et cetera. There's a
lot of slides coming in here at the end. Common database systems. 3 major database management systems and why to use. Oracle. I've heard of Oracle. Large commercial enterprise scale, very, very tweakable. MySQL, simpler but very fast and scalable, commercial open source. SQL Server, very nice from Microsoft, also access. Many other smaller projects free and open source. HSQL, SQLite, Postgres.
A lot of products out there that you may encounter. We're going to be using SQLite. SQLite's a little tiny database server, and it's built into so many things, and that's why we like it. But if you're going to work at a large organization, you could easily run into Oracle, which is the #1 commercial product. Microsoft has a thing called SQL Server, which is a commercial product, and it's also very popular and very effective. The more popular open source, there's things called Postgres, there's MySQL, and MySQL recently was sort of bought by Oracle, and there is a copy of that called MariaDB that doesn't belong to Oracle, MariaDB. And so most of the SQL that we're going to learn is common across these database systems because SQL is a standard, but then there are parts that weren't part of the original standard where each database vendor has done things a little bit different, but there is a core common subset that does the basic create, read, update, and delete operations. So SQLite is a very popular. You probably have it in your cell phone 10, 12 times. Your web browser has a database engine in it. Your car has a few databases in it. And so SQLite is what's called an embedded database system. Python comes built in your cell phone 10, 12 times. Your web browser has a database engine in it. Your car has a few databases in it. And so SQLite is what's called an embedded database system. Python comes built in with it. You just import SQLite 3 and away you go. And so it's a very, very popular because it's free, it's open source, and it's such a tiny little piece of software that you just include it in other pieces of software and use it to solve the data management problems of those pieces of software. Like your browser might use SQLite to store your bookmarks. Now you think, oh, there's only how many bookmarks can you have? But what if there you need it to be fast? And what if there's like people that have 10,000 bookmarks? There probably are. Do you still want it fast? Do you want to be able to search? And so you get all that by using a database like SQLite. And so
SQLite browser. SQLite is a very popular database. It is free and fast and small. SQLite browser allows us to directly manipulate SQLite files. SQLitebrowser.org. SQLite is embedded in Python and any number of other languages.
So again, we're going to encourage you to download the SQLite browser so you can follow along with what we're going to do coming up next. And so here is the SQLite browser. Here's what it looks like. And it's just a desktop application. And coming up next, we'll start playing with this desktop application and see how it works.
Oh my word. All right. So, we have the browser, which is not a primary database structure, or excuse me, primary data structure in the database. Index, table, row, column, index. Boom. All right. That is going to do it for today, everybody. Thank you so much for watching. If you enjoyed this video, please like and subscribe. Have a great weekend, everybody. I will be back Monday, streaming late Monday night. Probably. It might be during the day, Monday, but it also might be later at night. So I will be back after the weekend. Hope everybody has a great weekend. Please, did I already say please like and subscribe? Anyway, love God, love people, and I'll see you guys soon.